Hello, and welcome to another session on data mining. Today, we're going to talk about 12 ways you can impress the masses or fool the masses when you give your performance results for your machine learning algorithm. So, in the previous week, we've talked about how you can assess the performance of different types of algorithms in machine learning. And we talked about different types of metrics. We talked about different strategies such as cross validation that you can use for performance analysis of your machine learning algorithm. These 12 ways that we are going to discuss today are essentially some things that you should not do when you are reporting your results. So these 12 ways are going to be is a fun way for you to remember what to watch out for example, when you're reviewing a paper or when you're reporting your own results in machine learning. Okay, so let's jump right in. So let's say you want to design a machine learning algorithm that identifies whether a particular pizza is going to be popular or not. So if you have a problem like that, first you identify the problem, the underlying machine learning problem. That's the first step over here. Once you have done that, then you collect data. Let's say you do surveys and you collect features. The survey is going to tell you from a number of people whether they liked a certain pizza or not, and from the structure of the pizza itself, let's say you can extract different types of features. Those features can be such as like you can have what type of toppings does it use, right? And what type of cheese does it use? What's the type of base it has? And so on. So each pizza is going to become a single example. And then let's say you use the majority vote over the survey results that you have to classify whether a pizza is going to be popular or not. Okay, so you get a bunch of positive and a bunch of negative examples right over here. So that's the second step. And then what you do is you train a machine learning model, a classifier, let's say, to over the training data set that you have, and you now have a trained machine learning model. Then the next step that you do is you do a performance assessment of that or a validation. So you can use some held out data, you can do cross validation, you can have a completely unseen data set, you can have novel pizzas given to your machine learning model. Well, a machine learning model wouldn't be able to get pizza or eat pizza, but what you can do essentially is feed in the feature vector representation of that. So that's what goes in as input into your evaluation. And then you can calculate different types of metrics. Let's say you calculate the ROC curve or the area under the ROC curve. You can also do the PR analysis or precision recall. You can use accuracy. You can have different types of metrics that you can put in over in this step number 4. And once you're satisfied with that, you can perhaps develop a web server so that if people can upload what type of toppings they have on a pizza, it's essentially going to tell them whether they're going to like it or not. Okay, so let's say we can call this a pizza recommendation system. Okay, so the last step is deployment. However, in some circles like academics, for example, we are really interested in publishing those results as well, right? So there's another goal that we have, and sometimes like this takes precedence over simple deployment. Although it shouldn't, like deployment should be the primary focus of whenever you develop a machine learning model, it should be deployable. However, also we want to get it published, and sometimes when you're trying to get those results published, there can be some things we see that they're not people don't pay too much attention to those when they're reporting these results. So these 12 ways are essentially based on what patterns we've observed in such publications. So sometimes people overestimate the performance of their system. So they actually report that the system is let's say 90% accurate when in practice it may not be usable at all. So these 12 ways are essentially there to help you uh, to what to look out for when you're reading papers or when you're reporting your own results. Okay, moving on. So if you ever like what is the impact of overselling a system? So if the performance is not good, but you like or someone else, let's say, reports that the performance is 99%, when in practice that system is not usable, then that leads to a reproducibility crisis in that field. So because people will not be able to reconstruct your results, or you can see that systems will not be usable. So that gives a bad name to the field in general. And machine learning has a reproducibility crisis. It's a very well recognized feature of the field that there are people or who have mistakenly probably reported their results which are overestimates of the problem of the underlying performance of their system. So you can read more about that, about the reproducibility crisis. For example, this is an example. If you train a neural network, let's say to classify between ships, horses, deer, or all of these different types of animals, you can have a system that is particularly accurate, but then some people try to test the robustness of the system. And what they were able to find is that if you change a single pixel within an image, so if you, let's say, change a pixel over here, if you change the pixel over here, a pixel over here, then the label of the predicted label of the system. So if the original label for this particular example was a ship, so the system identifies it as a ship, which is correct. But if you make this change, a single pixel change, then the label gets changed to a car, let's say, which is bad, right? A single pixel should not have that much of an impact. I think we've talked about uh, regularization, and this is one of the failures when you don't have a very well regularized system, which is also not well, it's accurate over the training data set, probably, and but it wouldn't be able to generalize, or it doesn't have enough robustness uh, so that a single pixel attack on this system allows changing the predicted label. So instead of classifying it as a dog, if you change one pixel over here, suddenly the system is calling it a cat. Now these systems are being used to, let's say, in automated driving. Let's say if someone changes a single pixel in a stop sign, imagine what the impact of this can be, right? So we really want to test the robustness of our systems before we deploy them, so we don't have such problems, right? Other than that, it can really stunt the growth of the field as well. If someone reports performance results that are overestimates, then people typically stop using the same data set or the same problem for development of new methods or for evaluation of new methods, and that leads to stunted growth in the field, which is another problem. So although it seems really good that we have a system now that can classify 99% accuracy, but we also need to test it extensively, both its accuracy and its robustness, before we want to deploy it, so that we don't end up with any such results. And if you end up being a poor graduate student or a PhD student, and you have your task to work on a certain classification problem, and someone overestimates their results in a paper, and you're trying to reproduce that, and you won't be able to do that, you might end up with some psychological issues. And this is a fact. As a PhD supervisor myself, I've seen people struggle with similar problems, and it's something that we should watch out for. So please go whenever you are reporting your results, try to do a very robust analysis of your results. Okay, so but let's say we don't want to do that, and we want to oversell our methods. Not recommended, but what if you wanted to do that? Again, these are things that you should not be doing, right? But this is a fun way of remembering those. The first way you can do that is that you pick a biased accuracy metric. And we saw that every performance metric that we talked about, accuracy, we talked about AUC, ROC, we talked about precision recall curves, all of those have underlying assumption bias. So by accuracy metric, I mean any performance metric, performance assessment metric that you have. And it can be each metric has some biases in it. For example, accuracy, we've talked about its limitations, and we've talked about the limitations of precision recall curves. We talked about limitations of AUC, ROC as a performance metric. So if you apply these metrics where they should not be applied, you are essentially using doing this. And by you, I mean anyone, okay, myself included. Okay, so let's say if you walk into a company for an interview, and they say that you ask them the question of the interview, not a good question to ask in an interview, but maybe you're selected and you want to do some salary negotiation, and you ask the question, what would be my starting salary be? And the answer comes out to be, I'll put it this way, our average starting salary is about $80,000. Now, that is a correct statement. There's nothing wrong with it. But if you look a bit deeper, the reason the average is 80,000 is because the CEO's son gets 430,000, and then all other coworkers, including yourself, are going to get 30,000. And if you average them out, you essentially end up with 80,000. So you wouldn't want to work for that company, right? Similarly, if you report accuracy results over an unbalanced data sets, so in which one of the examples, one of the classes dominates all the other ones, and you use accuracy, right? So for example, you want to detect whether a person has cancer because the prevalence rate of cancer is pretty low in the typical population. So the number of positive examples for that class is going to be pretty small, right? And if it's only 2%, and let's say your classifier classifies everything as positive, your accuracy would still be 98%, but that system will not be usable. This is an extreme example of biased accuracy metrics. There are other types of biases, and you should watch out for those. When you're reading a paper or when you're reporting your own results, it's always recommended that you look at the assumptions and limitations of the performance metric that is being used. Okay, so that's the long and short of it. Okay, so if you, for example, if you see a statement, our method shows 98% accuracy on test data, you first want to verify the set of assumptions that go along with accuracy, right? Or if you the report say that we have got a AUC ROC score of 0.98, please go ahead and take a look. If they report, for example, the precision recall curve that has a 90% is 90% the area under the precision recall curve, or the average precision is 90%, you may want to check whether they have used the positive class or the minority class as the positive class there, right? So those are sort of set of assumptions that you may want to check. The other way you can fool the masses is maximize the performance metric without cross validation. So typically what we do is we do a performance assessment we use cross validation to tune our hyperparameters, and then we can report our performance on an unseen test set, right? So tuning these hyperparameters, for example, the value of C or the value of the kernel that I should use, or the classifier that I should be using, those are all choices of hyperparameters that we can make, and ideally these should be made independent of the test set. And however, sometimes some people can forget that they are supposed to do it that way. And what they actually do, or they may do, is they choose a set of hyperparameters to train the model, they evaluate it on the test set, and then based on the performance of the test set, or let's say accuracy on the test set, they tune the hyperparameters. And if you do that, you end up with a final model that is now overfit to the test set. So that's a term that is being used. So it's not overfit to the training data set, it's overfit to the test, because you use the test data set as part of this, and that is a problem. So it's going to perform well on that particular test set, but it may perform very poorly on other real world examples when you deploy that system. Okay, so this is a code to help you remember that if you torture the data long enough, it will confess to anything. So this is one way of torturing your machine learning model or your data to get optimal performance out of it, although the system can be practically useless. Okay. The third way you can mess things up is, and again, by you, please don't take any offense. I just mean me. Okay. Indirectly use labeled information in validation, and this is one way that can happen. So let's say this is this is a pseudocode for how you run your machine learning models. Let's say you initialize your model and then you run a cross validation fold. So you do a loop over all the folds. You train the training data. You use the training data for a certain fold to train the model, and then you evaluate it over the test data set, and then you append the results. But if you look closely, there is something fishy going on over here. The model is initialized before this loop, right? Then you trained within each fold. Now, unless the train function reinitializes the model as a fresh model, what can happen is the model can accumulate the training cycles that it's getting, and that can lead to the final score being pretty high. So if you see numbers like this, that once you train your classifier, you have, let's say, 70% accuracy in the first fold, but your accuracy improves across multiple folds, and then you get the average accuracy, which is pretty high. Please go ahead and look if there is something like this going on. Are you initializing your model within each fold or not? You should ideally be doing that. So if you use the built-in sklearn libraries, and you use the cross-validation that they provide, please make sure and read the documentation whether they reinitialize the model within each fold or not. Okay, so that's something for you to check. But this is one way that the test labels are actually being used in this way, okay, as part of the training. So these become the test labels of one fold become part of the training labels of the next one. But in the next fold, then you'll be evaluating your performance over the test fold, right? So that's going to be a problem. Just like underlying, each performance metric has some underlying assumptions. Different machine learning models can have underlying assumptions, especially during their performance assessment. For example, one of the assumptions when we make when we are evaluating machine learning models is that the training data set that we use, the test examples we have for a given, let's say, cross validation field, the test examples have not got nothing to do with the training examples. So they're independent of the training examples. However, in certain cases, that assumption may not be valid. So let me give you an example. Let's say you want to predict the intensity of a hurricane using satellite images, and this is something that I've worked with. And what happens is that you track the same hurricane over a period of time. So you get multiple images of that hurricane over a period of time as it travels through the ocean from one point to the other. So you can get multiple satellite pictures. And let's say you've got ground truth data for that. For each picture that you have, you also have the intensity of that hurricane. And let's say we got two hurricanes. We have Hurricane A and Hurricane B, and we can do a 50% train test split. What that means, one way of doing that is that I can use 50% of the training data for Hurricane A as part of the training data set, and I can use 50% of the training data for Hurricane B as the training data set. Okay. And then the remaining data of Hurricane A and Hurricane B ends up in the test data set. Now, this is tricky because, or this is a problem because now we have test data, a certain set of examples of the test data are actually a part of the training data set. Not directly, they aren't exact duplicates of each other, but they have something associated very closely. A test example can have something very closely associated with the training data set. So let's say if you've got an image of a hurricane at a certain time, let's say uh, you have you have something like this one. Sorry. So let's say if you have got, I'm sorry, I seem to have lost my pen here. But I think what I'm trying to say is that let's say if you use this image in the training data set, and then you use the next time step image in the test data set. Now, because these two images are going to be very similar because they're going to be taken only, let's say, 2 hours apart or 6 hours apart, the intensity of the hurricane is not going to change much. And because you have one example in the training data set, your test example is going to be predicted very accurately. But and you would get really good performance measures. You could very high performance and very high accuracy. But that system is not going to be particularly useful in practice because in practice you would get a completely different hurricane for which you have no associated training data. So this is what it means that you have. It's not a direct train test overlap, but it's a more subtle form of the same thing, right? So a part of this data set, let's say you can have these three images in training, and then you can have these three images in testing, and you can get very good performance metrics for Hurricane A. But the real test of the system is going to be how it performs on an unseen hurricane or data for an unseen hurricane. So there may be groups of examples of closely related examples in the data set, and if you just do a random split between them, that's probably not going to be a very good idea because that can lead to an overestimate of the generalization performance of your system. Okay, so that is the problem with that. Do watch out for that. And one of the things you can ask when you're reading a paper or when you are reporting your own result and you do a performance or a test split, always make sure that you test it under the same situation as the system, as you expect the system to perform or to be deployed. So take the deployment of the system, keep that in mind, and then evaluate it under the same scenario. So you get some realistic estimates. Okay, I hope this helps. Let's move on. The next step is the next way you can fool the masses. Again, you shouldn't, but if you plan to, be evil. Do not compare performance with a baseline classifier. So one of the problems that has recently emerged is that people don't compare their performance analysis to a baseline or a very simple classifier, which is not a good idea. You should always so most of the people, for example, if I'm developing a machine learning model, then I'll just try to incorporate the latest and greatest machine learning model out there on my performance, let's say the deepest of the neural networks, and see what performance statistics it gives without comparing it to a simple model. So that is one of the problems that has emerged recently in the field, and it's something that we need to watch out for. So if you are designing a machine learning algorithm, what you need to do is to always develop the baseline machine learning model first, and then you can improve that machine learning model by addition of features or using a more sophisticated machine learning model or a classifier to achieve better prediction performance. So the thing that you shouldn't do is that you start with the most complex and in method. You should start with the baseline method, the simplest one that you can find, and you should always check if the simpler method, what is the performance of that. So an example of that that we tried with is detection of nuclei or cells within a histopathology image. We developed a very simple machine learning model that was actually giving the same performance as more sophisticated deep learning machine learning models out there in terms of their F1 scores and their precision recall values, as you can see over here. So it's always a good idea that you do this sort of analysis. Start with a simple classifier and then move on to a more complicated one. Okay. Compare your method with unoptimized versions of other methods or ones that have been trained using different data. That's another way you try to over optimize your own method while you don't extend the same courtesy to methods developed by others. Let's say if you develop your novel machine learning method and you want to write a paper about it, what you can do is you can overestimate or you can find optimal set of parameters for your model, but not do the same thing for other models, and that's gonna give lower results for others models, even though they might be better than what you've just proposed or what I've just proposed, but we'll never find out, right? So the one way is like always try to do a head-to-head or an apples-to-apples comparison. So use the things that you shouldn't do is use best parameters for your model, but forget to optimize other models. And one thing, always make sure that the cross-validation protocol or whatever performance evaluation protocol you use for comparing different machine learning models or classifiers, those are the same for all types of machine learning models that you use in the comparison. Okay, so you have a head-to-head comparison, and you shouldn't compare the performance of the same model over two different data sets with two different validation protocols as well. So an analysis only makes sense if it's done over the uh, same test set. Okay, and none of that test set has been used for training, right? So present your paper in a way that doesn't allow reproducibility. So for example, you're working on your assignment and you submit it, but we are not able to run it, right? So you'll not be scored very, you won't get a very high score. We should be able to run it. And that is what reproducibility means. And we should be able to get the same performance statistics that you get, right? So well, some now it's now people are more generous in giving out the code, but and it's always a good practice to, if you are publishing in an open access journal, to give people or if you're publishing your code open access, it's always a good idea because then you can get that accelerates the field further, right? Because your results are reproducible. So if you do not provide detailed performance results code or a web server, we never know what the true performance of your machine learning model is. So you just have a black box, you have a paper, but probably nothing more useful. And that leads to a reproducibility crisis. So that was first, like not first, but it was identified in one of the papers that in terms of reproducibility, that only a small fraction of papers are actually reproducible. You can get the same performance statistics as the authors reported. So that's not a good thing. We should actually aim for getting the same performance, whatever it is that has been reported in the paper, if you rerun those same experiments, right? Choose a performance metric irrelevant to the problem domain. Now, I've talked to you about some generic performance metrics like accuracy, and we talked about balanced accuracy. We talked about AUC-PR and AUC-ROC, right? However, those only make sense, or reporting that only makes sense if they are relevant to the problem domain. So, for example, if you're working with a pathologist or a biologist, and they ask you the question, for you develop a machine learning model for them. Okay, you have an ML model that takes in, let's say, a protein and determines what does the protein do, right? Let's say whether this protein is going to be able to stop coronavirus or not. So you've got a protein as an input in the form of its sequence, and then you want to predict whether it's going to be effective against SARS-CoV-2, right? So the objective of designing such a machine learning model is that we don't need to test each of these protein sequences for their effectiveness in the wet lab, as it is called, or experimentally, or do biological experiments to identify which proteins are actually going to be effective against SARS-CoV-2, for example. Now, the biologist is interested in how many proteins or genome or how many proteins should I test in the lab. Let's say you've got a list of 1,000 proteins. You give it to a machine learning model, and your machine learning model, let's say, identifies 30 of them which are good candidates for SARS-CoV-2, and then you can give that to your biologist, and then they can run experiments to experimentally verify whether they are effective against this virus or not, right? So what the question that they are asking is, how many proteins in this genome or should I test in the lab? And the answer is 30. But instead of giving that answer, if you say that our system has an accuracy of 99.97, it doesn't really mean anything to them. Okay, what they always look at the question that your customer is asking from your machine learning model, right? Or how is it going to be used in practice? So it's really important to understand the use case or the deployment use case of your system. How is it going to be used? And always use a metric that is relevant in that particular context. And if it's not, forget about it. Pick a metric that is, or design a metric that measures the performance of your system in that particular deployment context. Okay, so that's really important. If they're not able to interpret those results, if the domain experts are not able to interpret those results, it really doesn't make any sense, whatever metric you report, right? And then it's really important to analyze the sensitivity of your model to changes in data. So how much variation in my performance statistics can I expect if I change the test data by a small amount, right? Or if I test it on a different system, or so you test your system on a different data set, right? How much variation is there in terms of hyperparameter values, or how much variation is there in terms of randomness? So some classifiers can generate different boundaries or slightly different boundaries as the classification boundaries when you run them multiple times. So that leads to an inherent randomness in these classifiers. So what is the impact of that, right? We need to measure that. Your systems should not be like this at all, right? So they should not be very tightly coupled with a specific set of parameters. So there's a small change in your hyperparameter values. If you make that change, the whole performance statistics comes tearing down, right? We shouldn't have that. So if you want to fool the masses, then do not analyze the performance of your system conditions to minor changes in hyperparameter values or randomness in the folds or changes in the data. So if you don't do that, you're essentially not giving the truth or the true performance of your system. Similarly, some people say that the seed of the system, the machine learning model, as in terms of deep learning, is important, and we should always save that. That's not correct. That essentially means that it only gives certain performance statistics for that particular split of the training test data and for that particular initialization of the weights of, let's say, the neural network or any other model, and it might end up to be very sensitive to randomness. So that's something we do not want. We want to analyze the performance of the system, its accuracy or whatever metric you use. So if I run it multiple times, if it gives me a slightly different performance, that's okay. But I need to analyze how much variation or how much variance around the mean there is when I run the same experiment multiple times. So it's essential that you analyze that, right? Now, some people are really fan of statistical tests in machine learning, and they're really useful in certain contexts. But each statistical test that you use to analyze the performance of your machine learning model has certain underlying assumptions. For example, the performance statistic or the numbers that you're getting, for example, they must be distributed they must be Gaussian distributed, or they must be normally distributed, which may or may not be true. So sometimes people report statistical tests, the performance of a statistical test, even when the assumptions of those tests are not met. So that's wrong. We shouldn't be doing that. So, for example, let's take a look at this joke. I wonder which statistical test would be suitable for my data. And the inner me is just pick another one because that would make my paper look cool that I have done statistical analysis. It's always important to analyze the assumptions underlying that test. So one of the common assumptions that is violated is normality, so that the data or the performance statistic that you have is distributed according to the normal distribution. If it's not, you shouldn't be using those tests, okay? And then we can always impress or shock and awe our audience into submission using buzzwords and pretty plots, right? So if we have a paper that says modal, hyperspectral, convo residual, superpixel, blockchain, deep learning on a quantum computer, okay, we need to really tone it down a bit, right? So, and we can also impress people with pretty plots, right? However, the good thing about science is the truth eventually comes out, right? So, but it may take time, right? So, please always focus on the science. Always be honest with reporting these results, and you would be fine, right? Okay, and care only about publishing. Let go of the concept of generalization and practical use. When you're developing machine learning models, especially in academic settings, it's sometimes possible to feel a kind of disconnection. So, for example, I work on cancer imaging, and what I see is an image that is brought to me, but I don't see the patient whose tissue it is, right? And it's important to always keep that connection in mind so that I don't end up focusing all my energies to for publishing. I always keep in mind that the system that I'm working with impacts certain people, right? And it's something that would keep you grounded if you keep the bigger picture in mind all the time, right? At the same time, we must focus on trying to build a better machine learning model or that can be helpful, and that can only be achieved if you keep the concept of generalization and how that system is going to be deployed and how it's going to be used in practice in mind. Okay, if you don't do that, you've got a problem. So we shouldn't be focusing on impact factor only, right? We should be focusing on true impact as well, right? So we should make sure that whatever machine learning model that we are building has a practical impact and not just if we're not doing it, not publishing it for publishing's sake. Okay. So and a bonus way you can fool the masses, right? So no need to worry if your model makes sense or not, or whether it is interpretable or not. So if you have a machine learning model that generates some predictions, that's fine. You don't need to explain. You probably don't need to understand why it's making that prediction, right? So, well, wrong. We actually want systems to be interpretable. So we ideally want these systems to be able to explain why they make a certain prediction. So let's say if you've got a cancer image coming in and your system says that this person has, let's say, grade 3 cancer, why is the system making that prediction? And it's important to understand, and that's what it means. There's a slight difference between explainability and interpretability, and I leave you that out to you to find that difference. But the essence of it, we should ideally be able to explain the predictions of our system, okay, or the machine learning model, okay. The conclusion of all this talk that I've given and the paper that I'll be posting is when you're reviewing or supervising research studies, look out for these tactics, and especially if you're a student, it's really important. And these set of points can really help you critique a paper in machine learning, right? So I closed with this quote. It's the paper is available online, and you're welcome to read that. And I hope that these 12 ways that we have discussed would give you sort of a fun way to remember what you shouldn't be doing when reporting performance results in machine learning. Thank you.